Okay, welcome everybody. Thank you for coming to our last semester seminar. It's a great pleasure to welcome today Dr. De Silva from Pomona College in California. I think most of you know Dr. De Silva for his pioneering work in applied topology. He's studied at Cambridge and Oxford, where he got his PhD degree under Dr. Donaldson's supervision. He's also been associated with the Gunnar Carlson Research Group at Stanford for many years. And he also has the pioneering paper by him and Josh Tenenbaum on isomaps, which is highly cited and very well known in pattern recognition. And also, he's done a lot of work also on sensor networks, and particularly was honored by SIAM 50 Award in 2007 for his paper with Dr. Greist. He's currently an associate professor, newly associate professor in mathematics at Pomona College, and he also holds a Digitio chair at INRIA in Saclay, France. So it's a pleasure to have you here and tell us about some of these nice things that you've been doing on applied topology. Welcome and thank you.
Okay, thanks very much, Hamid, for the invitation to be here. Thank you all for being here. What I'd like to do, I've been working in applied topology for probably about 10 years now, starting with some work on, as I say, isomap with Josh Tenenbaum back about 10 years ago now. It's been a while since I really did that kind of work, but I was also working with Gunnar Carlson. Initially, I think, for me, the idea is that I have always been primarily a mathematician with interest in geometry and topology. And it's been a really pleasant development for me to see that over the last few years, there's really a huge growth in the application of algebraic topology. So these ideas about taking an object, what is its essential topological structure, how many holes does it have? And this is all, in mathematics, this goes back, well, it goes back to Euler in a way, but it goes back really to the early part of the 20th century when algebraic topology was first developed systematically. And in math classes, if you're a math major, you don't tend to do algebraic topology until your third year or your fourth year, or maybe in graduate school. And that's partly because the theoretical justification for these techniques does require some sophistication. But I think applying these techniques can be done really just using linear algebra, first of all, and can be done much earlier. And the things that these techniques are trying to capture are very much part of sort of the intuition of the human mind. We know, we look at an object, we know various things about its topology, whether it has a hole, whether two things are linked to each other. And so I think it's been very pleasing for me to see over the last few years how there has been a shared mission to bring these ideas to a much broader range of people, particularly for scientific applications. So I'll share a few of the projects that I've worked on. This is a talk that I gave about a year ago, maybe a year and a half ago. I haven't done very much new since then, so this really does cover the kinds of things I've been thinking about. There's a lot more going on that I won't be talking about. If you're interested in the field, there's a lot of particularly government-sponsored activity as well. There are some big grants, both from the NSF and from DARPA, that have supported this kind of work. So I begin by asking, what is topology? And the classic, or maybe not so classic, depending on whether this is a cheesy joke or not. It's a branch of mathematics which does not distinguish between a teacup and a bagel, meaning that they both have a hole that you can link a piece of thread through. The teacup has a handle, and the bagel has the middle of the bagel. That's one popular answer. Now, why do you do this? Well, mathematics, you could say, is, in most people's estimation, the common person's view of mathematics is that it's remorselessly quantitative. Right? In fact, people have some resistance to mathematics because people have some resistance to the idea of attaching numbers to things. Right? But topology gives answers to qualitative questions. And therefore, like those of us who work in this field believe that sometimes a topological answer is more appropriate than a purely numerical answer. Right? So this is a topological, this is a qualitative question. Well, I haven't said what the question is, but what's the question? The question is probably something like, can the little red dot escape from the maze? The answer is yes, because topologically it's the same as, those are topologically the same thing. Right? Now, how does it escape from the maze? Well, topology doesn't actually tell you at this point. Right? So there is, we're simplifying the question and getting a simplified answer. Which of these objects is different? Well, obviously that one. One particular field of point cloud topology comes into modern nonlinear statistics. So you can see those three, we call these point cloud data sets. And the human eye, by which I mean the human entire visual cognitive apparatus, which begins with the eye in this case, can look at these three pictures and instantly see, well, let's look at the top one. The top one is instantly, you know, we sort of infer that the structure is really a circle. We've sampled from it, and then there's been some noise. And so now we have to sort of remember that we had a circle or detect that we had a circle. And the other two are similar, right? So the basic mechanism that we try to use is this idea of Betti numbers and homology groups. So first class in algebraic topology that a person would do would cover these. And then you'd have to work a whole lot harder because it turns out that these invariants that we define, you need to show that they have a certain interpretation in pure mathematics that's totally rigorous, and that's why it takes several years for you to get to it. But the idea is, given a space X, I'll use my little pointer here if that's helpful. Given a space X, we assign various numbers. These are positive or non-negative integers, bk of x. And the k tells you the dimension in which you're trying to evaluate features. bk is the k-dimensional connectivity. Okay? It starts at b0, and it works its way up. Now, these are actually, what's important, maybe not for us in this talk, but what's important is that these are actually constructed as vector spaces. So the vector spaces are called hk of x. And these are vector spaces of independent k-dimensional holes or k-dimensional loops. And so then the bk of x is, what's the simplest thing you can do with a vector space? You can compute its dimension, and that'll tell you the number of independent loops. Let's give you some examples here. So here are some 4 examples of spaces. So for an object in 2-dimensional space, it's fairly simple. B0 is the number of connected components. So the first example has 2 connected components. So B0 is equal to 2. B1 is the number of holes. So the first example has no holes, but the second one, sort of, you know, this sort of Phantom of the Opera sort of face mask has 2 holes, and therefore B1 is equal to 2. Okay? In 3 dimensions, it becomes one step more subtle. So B0 is the number of components. Now there are 2 kinds of holes that you can get in a 3-dimensional object. Right? You can, let's imagine you have a solid wooden ball. You can drill a tunnel all the way through from one end to the other. Right? So that's what happens in a bagel. A bagel has a sort of a tunnel drilled through the middle. In fact, this first object is topologically a bagel and a teacup. And so there B1 is equal to 1 for that one tunnel. The other kind of hole you can do is you can just create a cavity in the middle. Right? So imagine this second object, this on the bottom right, as being like a hollow tennis ball. So inside there's a sort of sealed off cavern. So that's a different kind of hole. It's a 2-dimensional feature, and so there B2 is equal to 1, and B1 there is only 0 because there's no tunnel. Okay. Now, and in higher dimensions, you can, you don't just have B1 and B2. You have up to bk minus 1 if you're a subset of Rk. Right? So that's the basic idea. So I'm going to sketch a little bit how you calculate this, but really I think if you're interested properly in doing this, you may want to look at a sort of an introduction to algebraic topology. So the lesson of this is that you can calculate these quantities. Right now I've described them intuitively. The lesson is you can calculate these quantities using finite dimensional linear algebra. So what you do, so here might be a space. So this is an annulus, like a disk with a hole in it. So B0 is going to be 1 because there's one component, and B1 is also going to be 1 because there's one hole in it. The first step is you represent such an object as a simplicial complex. So you try to represent it as a union of triangles, tetrahedra, edges, vertices, edges, triangles, tetrahedra. Build it up that way. So then you have a discrete object that represents your original space. Right? From this, you can construct, so I'll rush through this a little bit. You can construct vector spaces. So C0 is the vector space generated by the vertices. C1 is the vector space generated by the edges. C2 is the vector space generated by the triangles. Right? Now that doesn't in itself contain any geometric information significantly, because any given object can be broken up into triangles in lots of different ways. So the number of triangles can vary depending on how you've broken it up. In order to get topological information, you want to construct these linear maps that are called the boundary maps. Okay, so the boundary map tells you if I have a triangle, what's the boundary of a triangle? It's the three edges around the triangle. Okay, what's the boundary of an edge? The boundary of an edge is the two vertices at the end of the edge. Okay. So you can think of that as a linear map. So if I have a collection of triangles, I can take its boundary, and that will give me a collection of edges. If I have two triangles next to each other, then the edges in the middle should cancel out. So you sort of set up your linear algebra so that happens. And then at the end, you end up being able to talk about cycles. So for example, this green, I don't know if it's easy to see, but the green collection of edges here, that's a cycle because there are no free, there's no dangling edges. Right? Everything just loops up. And in linear algebra terms, what that means is that, so for example, this edge that I'm highlighting there, it has two vertices. Here's one of the vertices. Now that vertex is a boundary of this edge, but it's also a boundary of this edge up here. And if you set the signs up correctly, those two numbers cancel out, and you get 0. And you can do the same for each of these edges. Each of these vertices lives at the end of two different edges, and therefore is not regarded as being on the boundary. Right? Whereas for this red object here, you see on the left, there is a dangling vertex, and so that is in the boundary of this collection of red edges, and on the right there's another dangling vertex. Right? So the green object is called a cycle. The purple object down here is also a cycle. And the distinction between them actually is that the green cycle here encircles a topological feature. So the green cycle encircles that hole, whereas the purple cycle doesn't enclose anything. Now what you can do is you can say, well, aha, consider these 5 triangles that are inside the purple cycle. And the boundary of those five triangles is the purple cycle. So the difference between the red and the green and the purple is as follows. The red is not a cycle because it has a dangling vertex, in fact 2 dangling vertices. The green and the purple are both cycles because they close up on themselves and they have no boundary. But the purple is itself less important because the purple is really the boundary of this collection of triangles. Whereas the green, there is no collection of triangles that gives you exactly this as a boundary. And so the green, out of these 3 sort of objects, the green is the one that survives and that we regard as being a feature. The green tells us about that hole in the middle. So all of this can be expressed in the language of linear algebra, which is why it makes it very computable. Okay, so now here I think I spell out a little bit what this means. I think I'll skip these slides and move forwards a little bit. I'll just show you this one. So you can see, for example, that collection of 5 edges is precisely the boundary. Is precisely the boundary of that collection of 5 triangles. And what that means is that that collection of 5 edges does not encircle any topological feature. Right? It's trivial. It's topologically trivial. Okay. Okay. Now, the one application of this is some work that I did with Rob Greist and Abu Bakr Mohammed way back in 2004, 2005. And this is this idea of using topology to study a particular problem in sensor networks. Okay, so I think a lot of you here will probably have much richer background than I do in sensor networks. In a sense, I was really just, the hired mathematician. I mean, both Rob and Abu Bakr have, this is not, they have very strong math skills themselves, but I was a person whose only skill was in mathematics, and I had to learn some of this sensor network stuff from them. So the idea is, illustrated by some pictures I stole from the internet. We deploy a large number of independent robotic agents, which could be as simple as a little light meter or a motion tracker or something. Just sort of hopefully very simple objects that don't require too much power, don't require too much, maybe don't in themselves do anything very sophisticated. But if there are a large number of them, and if you use the right algorithms, then you might hope that they can solve more complicated global problems, right? So that's sort of the idea. So in other words, the sensors themselves are simple, but they may well be capable of supporting, if you have a large number of them, supporting quite sophisticated algorithms. Okay? But you also want these algorithms to function at a local level if possible. Right? So we looked at something called the coverage problem. So two-dimensional domain bounded by a fence. Suppose it's peopled by, well, it's populated by robots. Okay, here's a bunch of robots. And each robot, so that's a robot off to the side there, has a coverage area. Now this might be a signal transmission outwards, or it might be receiving some, sensing some information sort of inwards, right? But it could be a cell phone tower, it could be a surveillance camera. We're going to assume, just because we do, that these are circular disks, the coverage regions. And so then the big question is, I have all of these robots, each of them has a coverage area. So the obvious question is the union of the coverage areas, does it cover the region that I care about? Here the answer appears to be yes, depending on, you can probably see some little red blobs there. So depending on the thickness of the ink, the answer is probably yes, but maybe not quite. Okay. Now, if you try to do this, so what's your first response to this problem? My first response would be something like this. How do we determine if the domain is covered? Right. Well, it would be helpful to know what the domain is. Right? That seems basic. Right? That's the domain, or whatever it is. Right? It would be helpful to know exactly where the robots are. Right? That seems another basic thing you would want to know. So that mesh grid that I put on there is supposed to infer maybe you have some coordinate system, maybe you have GPS or something. So you know the shape of the domain, you know the robots. Once you have that, you can imagine doing some sort of brute force or maybe clever brute, you know what the robots are, you just simulate the whole thing on a machine and just figure out that there are no gaps somewhere. And you can imagine that there might be more or less clever ways of doing this, right, with that kind of information. it would be a centralized calculation. So you'd have each robot beaming its information to like a mother robot in the middle there, who will then simulate the region and figure out whether you've covered this. So that's my first naive approach to a problem like this. It seems very doable. It doesn't seem all that, there might be some interest in the quality of the algorithm you use to do this. So what ended up happening with this work with Rob and Abu Bakr, I think this, the idea to do this came from both of them. And then as the hired mathematician, I helped them with the theorems, is to actually get rid of a lot of these assumptions, right? So you're supposed to think that this coverage problem, let's go back to the picture. It's a qualitative problem, right? Because what you're really saying is, here is my yellow region. All I want to know is whether that region reaches out to the boundary, right, and does not have any holes in the middle. If it has a hole in the middle, then I failed. If it has no holes in the middle and it covers the whole boundary, then I've won. Now, both of those assertions are purely topological assertions. And so what this now kind of dramatically allows us to do, if we use topology, is we can get rid of some of these seemingly obvious and seemingly necessary assumptions, right? So now we're going to do something where we're going to try to solve this problem with an unknown domain shape. We don't know what the domain is. We might have some regularity constraints. Like we don't want it to be all, so wiggly and narrow, and that we're going to somehow fool ourselves. But maybe not too much curvature on the boundary, not too ambiguous looking. So mild constraints. We're going to need some sort of geometric information, but we're going to use the kind of geometric information that a topologist cares about. So what does a topologist care about? A topologist cares about local neighborhood information, like proximity. A topologist cares, if I've got 2 points in my object that I'm looking at, are they close to each other or are they a long way away from each other? Right? So at a topological level, that's all that you need to know to answer topological questions. So for us, this will be crude proximity information. Any robot is capable, so each of the robots might have a number, a unique identifier, that's reasonable, and each of those is capable of identifying whether it's close to the fence and which of the other robots are close by. It'll ping around, see what's nearby. Robot 7's over here, robot 10 is over here. I don't know where robot 13 is, so I don't care, but here's robot 5, they're all nearby. So crude proximity information. And that's fundamentally topological, right? Now, in this version, we're going to use a centralized information gathering. We'll still have a mothership. There are people who have sort of articulated how to do this with more localized calculations, but I'm not going to. In our first draft of this, we didn't do this. So the assumptions are like this. So here's sort of roughly what one of these theorems look like. So we're going to suppose that each robot has a coverage radius, which is a circular disk of a fixed radius, RC, coverage radius, RC. Each robot can identify all those robots which are near it, and we needed for our original theorem. Now I don't know how visible. Yeah, there are these cyan. There are 2 cyan circles that are completely invisible. Yeah, but you can. The next couple of slides will make it a little easier to see. Each robot can recognize 2 levels of proximity. So the first 3 robots are very close, and this radius is called RS, short range. It's the strong, like they're strongly close, as it were. And then there's a more weaker range of robots that are moderately close, and this is the weak distance. So RC, RS, and RW. And then finally, each robot can recognize. So from these proximity information, you can actually build 2 graphs. You can see that there are thick edges and thin edges, and the thin edges are the weak proximity. is the weak proximity distance, and the thick edges are, you draw them between two robots that are very close to each other. So then we have some inequalities. So this is just comes from the geometry, relating the coverage radius, the strong radius, and the weak radius. We have some technical assumptions that the domain isn't too pinched, so that it doesn't have thin tunnels, right? And that the fence is not too wiggly. And then there is a test for global coverage, and I'm going to say it's a one-sided test, so which, let's say this in the language of statistics, I guess, or of hypothesis testing, which gives no false positives and not too many false negatives, right? So false positive, let's see. So false positive is, you input all the data, you ask your program, you ask your algorithm the question, is there coverage? The algorithm says yes. Now, what we wanted was, if it says yes, we wanted actually there to be guaranteed coverage, right? Now, if it says yes, and somehow there is no, somehow coverage is broken somewhere, then that's a false positive, because it says yes, but it was lying. And so we decided that we didn't want false positives, because if we'd got a positive, we wanted to be able to trust that for sure, 100% sure. But because we're working topologically rather than with detailed geometry, we have a trade-off between false positives and false negatives. So false negative is when my algorithm says, no, I can't tell you that there is coverage. But in some situations, there might accidentally be coverage, but it's just that the algorithm can't tell. So we've decided in our trade-off that false positives were unacceptable, but false negatives, as long as you didn't have too many of them, were okay. And so there is a test using algebraic topology. Let me show you roughly how this works in one dimension. So in one dimension, now our domain is like this horizontal domain. And my robots, I'm seeing them, they really look like little popsicle sticks. Those are the robots. And as before, each robot has a coverage area. And as you can see, they do, in this case, they do all cover. What I want to show you is how you can, so in this very simplified problem, how you can detect the coverage of this strip using a purely topological argument where you don't know where the robots are. Right? So this is really a thought experiment. This is sort of saying, in principle, in one dimension, how limited can you make the information that you work with to solve this problem? So we're going to simplify this a little and suppose that you can distinguish between the left buffer, which is blue, and the right buffer, which is red. I guess I'm using the word buffer in the sense of railway cars. They have little buffers at the end that stop them falling off the ends of the rail. Not in the computer science sense. So obviously we look at this and we see, yes, there is coverage, but I want to do this in a way where we don't really know where the robots are. So here's how we're going to do it. So I'm going to go through this once with this picture, and then I'm going to go through this once with a more conceptual picture where you don't see where the robots are. So what you do is you look at all the robots and you join them up if their coverage areas overlap. Right? So that's if they're within a certain distance locally, then you join them up. You see those gray lines? So those are the robots that can be joined up. Any robot that's too far away from a given robot is ignored and might not even be detected. Then you also have to figure out which robots are next to the boundary. Okay, so let's say they also know if they're close enough to the boundary. And then you look, so now some of them are blue, some of them are red, some of them are still green. Now all you need to do is to look for a path between blue and red. Right? If I have a path between blue and red, then even though I don't know exactly where the green robots are, I do know that I've covered every point in between green and red. That's the topology. Okay. So this is how this. Okay. So now I'm going to run this again. You've got to imagine that if you're the mother robot doing this calculation, all you can see is the bottom half of that screen. So all you can see is this. Now, we secretly know what's going on up top, but the mother robot just sees what's going on down here. So the mother robot has 9 robots here. They all report back and they say, ah, yes, robot 1 says I can see robot 8, and robot 2 says I can see robot 9. And so I draw, as mother robot, I draw the graph. I also now get feedback from robots, 4, 1, and 8, telling me where they're near. So I know that. And now, to me, it's a very simple problem of plotting the graph. Can I find a path from red to blue? Yes, I can. Yes, therefore, I have coverage. And I did all of this without knowing where anything was. Right? And for example, if there isn't coverage, then you get this. And of course, now you can see there is no path from red to blue. They're separated. So the two-dimensional coverage problem is fundamentally the same as this. Right? If you think about what we're doing here, we're really asking the question, is the blue component in an opposite component from the red component? That is a B0 calculation in algebraic topology, 2 different components. And if B0 is bigger than 1, then it means that I haven't connected blue to red. So similarly, in the two-dimensional case, we are now interested in B1. So I span all, first I have to make sure I span all the way around the boundary. Second of all, I do my algebraic topological computation with linear algebra, and that'll tell me if there is a hole or there is no hole. And then if there's a hole, then I don't have coverage. Well, I probably don't have coverage unless I've somehow gotten to false negative. If there is no hole, then I must have coverage. Okay? So let me, so this is how this works in 2 dimensions. So again, you've got to pretend that mother robot doesn't know where anything is, but I'm going to pretend just for simplicity that we do have a sequence of robots posted on the outside, right? At sufficiently close intervals that they do cover the outside edge. So this is analogous to the assumption that we could tell the red side of the fence from the blue side of the fence. It gives us some control over the boundary. It just makes the hypothesis simpler. It's not essential, but it means I can explain this a little bit more easily. What I now do is I consider a proximity graph. So here I draw edges between any pair of robots. It looks like a lot of edges here, but any given edge is only drawn between 2 edges that are close to each other. And now I ask myself, there's 2 ways to do this. Is there any B1? Are there any one-dimensional holes in this? But another way to do this is, can I find a collection of triangles that form a surface whose boundary is precisely the boundary of the fence? And I can do that in linear algebra, and the answer here is yes. So you can see what I have done based on this graph is I have found a collection of triangles whose boundary is precisely the edge of this fence. Right? And inside, there's no boundary. Inside, the triangles glue up one on one in a solid way. Okay? The answer is yes, I can, and therefore I do have coverage. Now, from this picture, there is actually one bonus. So you see that some of the, so I've created this collection of triangles. Not every vertex, so not every robot is implicated in this collection of triangles. If I highlight, the ones that I've highlighted in red are the ones that are the vertices of the triangles that I've used. And there are some other robots which don't really have anything to do with my chosen set of triangles. And so again, one of the consequences of this is you can say, I draw my graph, I find a spanning collection of triangles using linear algebra and algebraic topology. If I like, I can switch off all the robots that do not occur as vertices of these triangles. Because in fact, the existence of these triangles is telling me, yes, if I look at these triangles, then each triangle is covered provided its 3 vertex robots are switched on. Okay? So you get a little bit extra from this. Okay, great. Okay, so that's one of the applications I wanted to talk about. Let me talk about something else. I'm going to maybe skip the next few slides. Well, I won't completely skip them. I just want to draw, give you a little sort of sense of what's going on. So in this part of the slide, this part of the talk, I want to say a little bit about point cloud topology. Right? So point cloud topology is given a statistical data set, I want to be able to say what is its topological structure. Okay? Now, one very fundamental question is the question of clustering. Right? So I don't regard myself as an expert on clustering, but you can think of clustering as a topological problem. So here is my data set. That looks like it has one cluster, probably one cluster. And at a certain point, see that clearly has two clusters, right? And one of the big issues in trying to do topology to data sets, the theory of algebraic topology was designed for continuous spaces that are idealized. They're perfect. There are infinitely many points, and they have some continuity relation telling you what the shape is. Data sets are not perfect. They're noisy. They're discrete. And you can transition. I mean, if I asked you the question, so between here and here, when do we go from one component to two? You can see that it's a non-trivial question, right? It's not clear that you want to give a definitive answer in this case that's yes or no. It's not clear. Here it might be a little bit more clear, but you want to be able to give qualified answers. You want to maybe give answers with error bars, right? Or you want to say, well, it looks like it might be one component. It looks like it might be two components. There's some, it could be one or the other, and here is some measure of confidence that it is one or the other.
Another separation.
Say it again.
Would the topology be able to show you that the separation that you've shown is not the one that might be the most efficient?
It might. I mean, I guess because in a two-dimensional picture, I guess our human intuitions are probably correct, and then in looking at a higher dimensional space, then you'd probably turn to the topology rather than trying to do it by eyeball.
Because I would have split the data along a line at 45 degrees.
Oh, you would?
Yes, I would.
You'll be alone, Eddie.
No.
So anyway, let me tell you a little bit about the pipeline. So the original pipeline was simply to take your data set. To take your data set, you're going to suppose that data set really represents some idealized object, like this annulus here. You don't know the idealized object, but what you do know is the sample from it, which your scientific experiment you might regard it as giving you a collection of readings from some idealized parameter space. Right? That nature knows this idealized parameter space. You just know the measurements you've taken, which is some finite set of points. And what you do is from this set of points to try to construct a simplicial complex approximation. And notice this square in the middle is filled in, but it's darker, which means that it's filled in but with less confidence than maybe some of the outer shapes. Okay? And so what you want is, initially what we had, let me go back a little bit, is a pipeline where you read your data, you approximate it by a simplicial complex, just one shot. You hope that this simplicial complex represents the original space, and then you read off the Betti numbers. B0 is 1, B1 is 1, B2 is 0. That's harder to read from the blue font I've used. But this is not statistically robust, and so to get something statistically robust, you want something where you take your data, you build not a single complex, but like a simplicial complex or a cell complex where each cell has a certain confidence value, which I've tried to indicate by shading. So the darker it is, the less confident you are that it exists. And one way to think of this is you don't just have a single complex, but you have a nested increasing family of complexes. So the first cells that you put in are the cells that you're most confident about. So you will have some sort of rule, right? And so what I really want to emphasize is not the specific rule, because you can think of, like, here's one example. You can say, pick a set of vertices reasonably distributed throughout the data, right? Some sort of furthest point sampling or whatever to make it well separated. And then you have to ask yourself, when do I include an edge between the two edges, between two vertices? And that might be a measure of distance, or it might be distance plus are there lots of nearby data points to that edge. You can imagine, you can conceive of many different rules that would do this. Now, if I have 3 vertices, I could say, well, there are 3 edges that I might want. You know, if those edges exist, then you're able to ask the question, well, now I have 3 edges. Maybe the triangle in the middle gets filled in, or maybe it doesn't. And so then you would want some additional rule that would tell you whether that happens. Now, there are different constructions. There's things called the check complex, the RIPS complex, witness complexes. And they all are roughly trying to do the same thing. And so really what I'm going to talk about is the big picture. So no matter which method you use, the big picture will always look roughly like this in this model. And so we want some sort of quantitative topology. And so quantitative topology, the most successful theory of quantitative topology is something called persistent homology, which is due to Adelsbrunner, Lecce, and Zomerodian. I think I have a slide crediting them in a moment. And the idea is something like this. So you can see they're a little bit small. Maybe maybe this demo doesn't work very well. So you know what I'm going to try to do is I'm going to show you a different demo. One moment. Movies. Afra, witness.avi. So this is the kind of thing. This is a beautiful movie made by Afra Zomerodian for some research that Gunnar Carlson and I did. This movie I have shown many, many times at talks. It's an example of an 8-dimensional data set projected into 3 dimensions. And what I want to show you is the following process. So this is what I want you to have in mind. I'll play this twice because I think it's worth playing a couple of times. And the mathematics behind this is due to Afra Zomerodian, Herbert Adelsbrunner, who has been at Duke for the longest time, but I think he has now moved to Vienna, but he's one of the great researchers in this field, sort of right here. And Lecce, David Lecce is the 3rd author. So the technique is like this. We've got this data set. We're going to approximate this data set by an increasing sequence of topological spaces that are going to be simplicial complexes. So what you're going to see is vertices, edges, and triangles, and you're going to see them growing. Okay? As they grow, we're going to compute the topology. And the topology is going to be the number of components, the number of holes, and the number of 2-dimensional holes. I'm going to focus on the number of 1-dimensional holes. So you're going to be counting how many loops, how many independent loops does this object have. So let me play this a couple of times. We're going to run this for 2 different runs of the same data. Here we go. So here's the data. It's projected into 3D just so we can see it, but it's really 8-dimensional. Those are the vertices, and now watch it grow. So the strong witness complex is just one particular construction. So as our tolerance decreases, the thing grows. Right. Now, pause. You can pause this. Right. Now, what I'm also going to show you, maybe I'll move this out of the way, is at the bottom a barcode. So the barcode is telling you what is the topology of my object at any given point. So the horizontal axis is time. Like I'm growing the complex. The horizontal axis, this vertical line is going to slide across, and I have these intervals. Each interval is going to correspond to a feature, and when the slider hits the interval, that's when that feature appears for the first time. And when the slider rocks off the end of the interval, that's when it closes up and doesn't exist anymore. So I want you to focus especially, so right now there are a lot of little intervals at the beginning, and you can see there's 4 or 5, 1, 2, 3, 4, 5, maybe 5 or 6 different holes, and you can see that the slider is meeting 5 of these intervals. But as we move, right, so now the slider, there's 1 green interval here. So the first few holes have closed up, there's a new hole here that has appeared. That's going to be temporary too, because that's going to close up in a moment, right? Now, as you can see, I'm approaching something's about, so there's an event about to happen, which is that in a moment, one of those diagonal edges is going to come in, and we're going to get a big loop. Okay? There. Now we have the loop, and that interval has become activated. And that loop survives, and at a certain point, it's getting more and more filled in, and then suddenly, boom, it's gone. Right? There was a hole, now it gets filled in, now there's no longer a hole. So each feature has a birth time and a death time. Let me now we'll run another example with slightly more complicated topology. So derived from the same data set, but a different subset of it. You can see it's got more things going on. Now look at the slide at the bottom at the same time. As you can see, there are 5 substantial intervals down here. 1, 2, 3, 4, 5. Okay. Let me go back just to maybe here. So the idea is, given a data set that you believe has non-trivial topology, interesting topology, you run it through this algorithm that Afra and his collaborators, and then actually he also did some work with Gunnar Carlson on this. You run it through this algorithm that they developed, and the algorithm will spit out for you a barcode, which is this quantitative homology barcode. And the barcode will tell you the following thing. It will tell you what the features are, but it will also tell you the tolerances at which the features exist. And any given feature will come into birth at a certain point, and at some point eventually get filled in. So what the scientific user has to do, if they want to use this technology, is interface with the front end of this code. And many people have written persistence code by now, so there's many different ways to do this. And they have to learn how they, or decide how they want to interpret this barcode so as to draw scientific conclusions that make sense in the field that they're working in. The barcode will have usually vast numbers of intervals, most of which usually are going to be very short, and this you regard as non-robust topological information. You regard short intervals as being features that maybe pop into existence briefly, but they don't last very long because they get filled in. Long intervals you regard as being meaningful. So this particular data set has 5 long intervals, so you regard that as being a meaningful measurement from this data set. So maybe what I can now try to do is now go back to the main talk and say something about where this data came from. Okay. Let me check now. I have maybe about 7 minutes or so for the talk. Okay, great. So this will be my final example then, I think. So the visual image data, this is joint work with Gunnar, with Afra, and with Tigran Ishkanov, all at Stanford at a certain point in time. This is building off some really interesting work by Lee, Peterson, and Mumford, who were interested in the statistical properties of visual images. So there's a database by Van Hatteren where he went out and took lots of photographs of the natural environment, right? Both human and sort of forests and things, and lakes and that kind of thing, and created this big data set. So the idea is the visual system, we see things. Let's say you want to solve the vision problem. In other words, you get a computer to see things, and then the computer has to do various things like segment, identify objects, whatever, track. Now, of course, typically we give a pixel representation, like a rectangular pixel grid of information, to a computer. You can do other things like wavelet coefficients or whatever, but let's keep it simple. And of course, so let's say I have a screen with 1 million pixels on it. So this looks a little bit like R to the 1 million. It's a real vector space with 1 million coefficients. But actually, we know that we can natural images can be compressed because most vectors in R to the million. So if I take a pixel screen and I randomly assign a value to each pixel, then what's it going to look like? It's going to look like random noise. It's going to look like what your television shows you when there's no signal coming in. So most actual visual images betray very, very specific statistics. And the question is, what are those statistics? Right? And so when the human visual system does, solves its processing task that it has solved, it's doing so not on the basis of points in R to the million, but it's doing it on basis of some very low dimensional or very high codimensional subspace of this, which represents the kinds of features you actually see in real images. So Lee, Peterson, Mumford took the approach of trying to say, what can we say about the statistics of a random looking image at the smallest meaningful scale? So they said, well, let's look at the statistics. If you look at the statistics of individual points, probably that has just completely random, uniform or normal or something. And you don't get any spatial information. So to get spatial information, they said, well, let's look at 3x3 patches. Maybe we can say, if there are going to be correlations between nearby pixels usually, because when you look at a scene, normally each pixel is the same color as the next unless there's a radical transition. Okay? And so going up to 3x3 gives us a little chance to get a little bit of geometry in here. So it turns out that so this is a 9-dimensional space, but what you can do is you can normalize by the average brightness, and so that makes an 8-dimensional space. You subtract the mean intensity, and then you also what the obvious thing turned out to be true, which is that most 3x3 patches were essentially low contrast, essentially constant. Right? You look, I look at this white screen. Yep, essentially constant. So the vast majority of the data satisfies this, and so what they did was they thresholded away from the low contrast patches and kept only the high contrast patches, and then they rescaled to normalize the contrast to unit, whatever, in some norm. And so now you have a 7-dimensional, so a unit sphere in 8-dimensional space. So you have a 7-dimensional sphere. The basis of this 8-dimensional space can, this is a basis, perfectly good basis. This comes from the discrete cosine sort of representation, cosine transform. And now you have, looking at your data set and looking at high contrast patches, you have some distribution of points on the unit 7 sphere. And so the interest is in where are the most dense parts of this distribution. And one conjecture that you had, so what they found was that the distribution of patches does cover the entire sphere, but there are certain high density regions, and one model for these high density regions, you'd expect edges. So when you see an edge, that represents itself as a, as a rasterized anti-aliased image like this. Sorry, as an anti-aliased image on the side here. And there are 2 parameters, right? So for given an edge, the primary parameter of the edge is the angle. So there's an angle theta. And then there's a sort of, how far across have you gone? So topologically, the collection of edges is an annulus, and you expect to see an annulus. Right? And if it is true that the densest part of the data is edge features, then you expect to see a dense annulus, and you could hopefully detect that topologically. So we try to do this. I'm going to sort of skip through a little bit and say that there is a difficulty in deciding what you mean by the densest part of the region, because what you have to do is you have to take the data, you have to smooth the data, and then you have to threshold, right? But there are different smoothing parameters. So you can smooth it very coarsely, and then you will see that you'll get a very coarse function, and if you threshold on that coarse function, you will get, here is the region that's approximately the most dense, and you'll get some answer. So that might be, for example, the bottom, imagine the bottom line, the k equals 500 line here. This is a very coarse smoothing, and I thresholded it from 100%, 50% down to 10%. And these are the densest parts of the data with that coarse thresholding. But on the other hand, you can also smooth using a very fine smoothing parameter, and you get something that looks quite different. You get sort of, you see finer information. And you can see this is what the sort of effect of smoothing does, is as you smooth, you see the annulus, but then later you just see a blob, right? And so you have to be careful. And it turned out that, and the movie that we just showed was 2 different examples from this. If you use a very smooth scaling parameter, you do indeed see the annulus. That's really exactly what the data looks like. But if you use a finer grained smoothing, you find that there are actually other features that are also visible. Right? Now here it looks like it's a cross, but you've got to remember this is a projection into 2 dimensions from 8 dimensions. And this is exactly where we get our 5 significant features that I showed you on the earlier plot. Whereas in the coarse version, you only get 1 annulus, so you only get 1 significant feature. And the example that the explanation for this is that actually, as well as the main annulus consisting of edge features, it turned out that this data also had secondary concentrations on 2 other circles. And the 2 circles correspond to all possible vertical features. So that's this blue circle here, right? All possible features with vertical symmetry and all possible features with horizontal symmetry. And that makes sense if you look at the real world and you take your photographs in an orthogonal way. You see a lot of vertical and horizontal lines, even in a non-human environment. You see trees and lakes and things like that. And that, to us, I think, was a vindication, because we would never have come across this model. We would never have sort of thought, identified this model without first doing the topological. We did the topological analysis. We expected a single circle. At a coarse scale, we found a single circle, but at a fine scale, we found these 5 different features. And the sensible explanation for the 5 features, which we were able to corroborate, was this model with 3 different circles. It's hard to see here, but the B1 of this object in 4 dimensions is actually 5. There are 5 independent cycles in here, and that leads us to this model. And so that was, in some sense, our perfect pipeline. We had an expected conclusion. We did some topology. The topology was unexpected, and it led us to think of a more refined model. There is, if you go a little bit further, no, I didn't have a slide for it. There is a more refined Klein-Bottle model that you get when you allow your camera to rotate freely. But statistically, we haven't managed to get that to be very significant, and so I don't think I want to say very much about that. But I think that's probably a good place to stop. Thanks.
About the two-dimensional central network. Can you go to the slide of the last page of the central network?
Tell me when to start. Here?
No. It's one slide before the continuous versus discrete.
This one here? Back.
Back. Oh yeah, right, this one.
Okay, great.
Yeah. So you just said that we will get a bonus to see that actually not all the vertices are required to cover the whole boundary, right?
Right.
So to me, it seems the choice of triangle here is not unique, right?
Exactly. That's right. Exactly.
So is there any topological method that will allow us to find what is the least number of vertices to cover the whole area?
Yes, so there's people who work on this. Ali Jadbabai, who is at Penn, UPenn, he and some of his collaborators, you can try to optimize this. A priori, it's a very difficult optimization problem, but what they do is, it's really an L0 optimization. Right? You want to find the solution to some linear system with a minimum number of non-zero coefficients. So what they do is they relax it to an L1 optimization problem, which you can then do by standard convex methods. And then they have some theorems that tell you that in some situations, it's just like this kind of compressed sensing kind of technology that says, in some situations, your L1 optimization is in fact also the L0 solution. I'm not an expert on when that happens or what the theorems are, but yes, so you can. It's a totally natural thing to want to do. Yeah.
So you said there are no false positives. That's good, and you're guaranteed not to have any false positives. But do you have any characterization of when you get false negatives, or do you have any? Is there any way of sort of statistically measuring how good the algorithm is with respect to false?
Yes. So here's the best answer that we have, which is it isn't very statistical, but at least it's the mathematically tightest answer we've come across. You can ask yourself how robust this is to a change in the covering radius, right? So you can say, so let's say my coverage radius is a certain amount, and now let's say I increase the covering radius. So now if I increase the covering radius, I'm most likely to, obviously more likely to have coverage, right? And so with the false negatives, I think the idea is that if you do have a genuine negative, let's see, what's the best way to say this? If I have a false negative, then that false negative will necessarily become a positive if I increase my coverage radius by, there's some quantity, I think it might be square root of 3 or something like that, right? So that's the most, so in other words, if I do have a false negative, that false negative will disappear if I increase the covering radius by a certain amount. And so then that's, in some sense, that's sort of a measure of the robustness of this method when it fails. We haven't translated that into a statistical estimate.
So let me ask you a different question then. So essentially saying if you increase the coverage by root 3, then false negative will turn to a positive. So does this increase the computational complexity of your algorithm? Does it do anything to your running time of the algorithm?
Actually, no, that turns out to be one of the nice things about, so this process of increasing the radius to root 3 is a persistent homology process. You have two different radii, you compute homology at one and you compute homology at another radius and you somehow compare them. And one of the nice things about the persistent homology algorithm is that it is no worse to calculate a persistent homology where you're considering several different scales at once. It's no worse calculating that than calculating the topology at a single scale. It's still order n cubed, and the methods are fundamentally the same, right? So
then why would you start with the larger covering radius, or is that really a property of the sensor that is out there?
Yeah, your sensors will have whatever radius they have, right?
Okay.
So it's really just a conceptual way of saying, as long as the ratio between, if you say that the ratio between the two radii is not too large, then it's sort of saying, well, we might get false negatives, but they're not going to be that, they're, the ones that do have coverage, they're not that far off from being detectable negatives, if that makes sense, or detectable as positives. So that's mathematically the tightest. In response to the topology itself, that's the tightest way to control the negatives. But you don't actually have coverage at that larger scale. You just have coverage at one original scale.
So for this problem, for example, to solve this problem, it's not really necessary that you know the fence, is it?
Right, so if you don't know the fence, then there's a more elaborate calculation that you do. You still need to know whether you're proximate to the fence, and then there are some other parameters that, because you're measuring whether there's a hole, but you could have all the sensors in one particular. What you really want to know is there a hole with respect to the sensors that are close to the fence, and so you need to be able to say, yes, I can track a loop around the fence, and I can see whether that loop is contractible or has a hole inside it.
Yeah, we've done some of that robotic stuff to fill in the hole.
Right, and then you can, if you identify it,
You can fill it in.
But so let me put this problem, this question that's like in the previous thought process you had in the previous slide.
This one was?
Before that. the one-dimensional case, where
Yes.
we had the start process, right? And in this case, you said if you can find a path from blue to red, then we are connected.
Right.
So, but I can also say whether if it's an equivalent test to do whether the graph is connected, that would be sufficient, right? And in that case, we don't necessarily have to know which are the fence nodes.
But if the fence is like this and it's connected, but then there's a big hole beside them.
So it's not just exactly. So it's not just connected, but blue is connected to red, and that you get from fence information. Right, because if all the nodes were slumped against one side, then the graph would be connected, but it would just be connected near red, and that wouldn't give you any guarantee of coverage.
Okay.
So it's exactly analogous. It's sort of knowing the boundary is exactly analogous. Now you can get away with something weaker, but you have to do a little bit more algebraic topology, so I didn't want to talk about how you do that. And you can't get away with too much less. Right? You still have to be able to track with, have some information about what's near the boundary or isn't near the boundary.
Shane?
So from the topological signature like Betty numbers, you know the number of the connectivity at different dimensions. But say now I want to look for where exactly are the boundaries for, say, holes in R2. So is there any effective method to...
Oh, so then it's the same question that you were asking where you look...
When it exists.
Exactly. You look for minimal one cycles. So if there is a hole, that means that the boundary cycle is an essential feature because it can't be collapsed to zero if there is a hole. So if there is a hole, you look for the L0 minimal representative of that feature. So the L0 minimum is the collection of edges that encircles all the holes which have as few coefficients as possible, right? As few edges. So then you have to try to, so this L0 optimization is of course, NP hard or whatever, but you relax it to L1, and sometimes you have a theorem that says that in those cases, in certain cases, the L1 optimum is also is the L0 optimum. And then now you have these tight holes that you can then try to fill in. Right? That's
Pretty much, and then if you go outside, then there's no connectivity. So you've moved into a hole, so you really should move back, right? And of course, they're not perfect circles. If you use actual sensors, they're not perfect circles. And that increases the complexity of the problem.
Any other questions? Yes.
Just about, do you ever deal with data that's at singularities or anything like that in any sort of objects? Or?
Oh, so you mean like, so you can imagine data sampled from a manifold, but then you can imagine data sampled from a manifold with self-intersection, that kind of thing? Yeah, so people do that sort of work. And Dmitry Morozov has some work on local, rather than estimating the topology, you can estimate the localized topology. So you take a point and you take a little disk around it, and then does it look like a piece of manifold, or does it look like some more complicated singularity? I don't know if people have done very much with it, but I think there's another group, maybe John Hera and Paul Bendick, who are at Duke, I guess. They work on, there's a wonderful pure algebraic topology theory called intersection homology.
Yeah, that's what I was wondering if you use those.
And so those folks, I think Paul, for his PhD thesis, was working on implementing intersection homology for point cloud data. So I think he's sort of a good expert to ask about that. I mean, the truth is actually that any piece of algebraic topological machinery, Steenrod squares or cohomology cup products, us algebraic topologists somehow we want to do this, but whether we actually do it or not depends on whether we feel that it's, whether we have good enough programmers and whether we feel that it's going to go somewhere and whether the theory is supportable. All of the theory needs to be supportable in this robust framework, right? The thing that makes persistent homology so important is that homology by itself is totally non-robust, and to be able to do anything with real data sets, you need some sort of barcode or something that gives you, is this one component or is it two? You don't know when it continuously can transform from one to the other, so you really need some sort of error bar or some sort of confidence bar. And so for things like cup products and Steenrod squares, it's just kind of less clear what the best framework for that is.
All right. Any other questions? All right. If not, let's thank our speaker.
Thank you all very much.
So we're reconvening.